Maxwell, can you hear me? Professor, I had a question on the homework. One of the questions talks about ICO.
Mm-hmm.
Seems to be the reverse.
Yeah.
This current on the collector side junction.
Yeah.
So we actually see it defined in the book, and I actually couldn't find it very well defined anywhere.
ICO means with the other, it's a reverse saturation current between the collector base junction with the emitter disconnected, open circuited.
So
it's just, yeah. So just treat the PN junction between the collector and the base as a diode.
Mm-hmm.
And that's your reverse saturation current for that PN junction.
So it includes electrons and holes?
Yes. Yeah. Just like a diode. Okay, good morning. Let's get started. I'm going to quickly wrap up our discussion about bipolar junction transistors and then jump into our final topic of optoelectronics. So over here, we are looking at a cross-section of an N plus PN emitter base collector BJT. So far, we've been discussing BJTs in the context of PNP devices because we use PNPs because it's nice that the flow of holes corresponds to the same direction of the current vector. With electrons, of course, it's opposite because NPNs are more common than PNPs because they have higher performance because of the higher electron mobilities, okay? But it's the same physics, just in the case of the NPNs, remember that the current vectors for the electrons point opposite to the flow of the electrons, obviously, okay? With that in mind, let's review the basic physics that you will be responsible for in the final exams. And these are the DC characteristics in steady state and these important concepts of emitter injection efficiency and base transport factor. So over here, I am showing the biasing and the corresponding band diagram in the so-called normal active mode of operation. And what that means is the emitter base junction is forward biased and the collector base junction is reverse biased. And that's reflected in the band diagram where you see that the potential barrier between the emitter and the base is reduced by whatever the forward bias is, VEB, while that between the collector and the base is increased by whatever the reverse bias, VCB, is, okay? And the way a BJT operates is, because I've reduced the emitter to base potential barrier, it makes it easier for electrons to be injected from the emitter into the base, okay? And if the base is very, very narrow meaning the base width is short compared to the diffusion length of electrons in the p-type base, these injected electrons will diffuse across, and hopefully most of them will survive the journey across the narrow base and appear at the collector base junction, where of course, as far as the collector base reverse bias junction is concerned, these now correspond to minority carrier electrons that have been injected by the emitter base junction. and therefore they'll be swept right across. Okay, so I'm increasing the supply of carriers, and therefore the effective leakage current of this reverse bias collector base junction. Okay, so that corresponds to my most important current component of electrons flowing out at the collector. Okay, so I see, of course, remember, of course, that the current vector actually points opposite to that, but just for the sake of clarity, I'll show the vectors in terms of the particle flow, the electron flow. Okay, so the electrons are flowing out this way, but of course the current is opposite to that. Okay, so this is the most important current component. Okay, because that will be my useful output current at the collector. The other current components that I'll discuss are kind of wasteful current components. Now, what are those? Well, one of them is the back injection of holes from the p-type base into the emitter. Okay, now that's a waste because clearly these back injected holes cannot contribute to the output collector current. Okay, and that then allowed us to define what's called the emitter injection efficiency gamma, which is the useful current in this direction due to IEN over the total current of the emitter, which is IEN plus IEP. That's a bad part, right? So that's a bad part. This is a good part, okay? And you'd want that number to be as close to 1 as possible by basically cutting back on the IEP. Now, how do you do that? Well, the way you do that is by increasing the emitter doping, and you make that N plus, because that then reduces the minority carrier hole concentration in the emitter, and that quenches this component, okay? What you'd want is to increase this component, the useful current, right? How do I do that? Well, you don't do that by increasing the emitter doping, as I've repeated many, many times. You do that instead by reducing the base doping, okay? So you want the base to be more lightly doped than the emitter, and that's reflected in the band diagram. You see that the Fermi level in the emitter is closer to the conduction band than the Fermi level to the valence band separation in the base, all right? However, as I'll point out in a second, there's limits as to how much you can reduce the base doping in order to increase the IEN, okay? Once again, the vectors that I'm showing over here correspond to the particle flow, okay? The actual current vector actually points opposite to that. Don't confuse that. All right, so there's limits as to how much you can reduce the base doping. What are some of those limits? Well, clearly, if my base doping is reduced at the base collector reverse bias junction, this depletion region will extend more and more into the base, and therefore the neutral part of the base, which is from this junction depletion edge to this depletion edge, will become shallower, shorter and shorter, and for these gradient of this carrier distribution will become steeper and steeper, meaning that if I plot IC as a function of say VCE, the current doesn't saturate but goes up, and that's of course the so-called early effect, and that's a bad thing because it's kind of like dibble in a MOSFET. It reduces your output impedance. All right. The other reason why you can't keep reducing the base doping is clearly if I reduce the base doping, my base series resistance is going to keep increasing, right? And that's not good because if you remember what we discussed at the end of the last class, and you look at the equivalent circuit, we saw that the base has an effective parasitic resistance RB, which is shown in a simplified model over here, and a more elaborate model down below. This is a so-called hybrid pi model. Hybrid pi model, because the circuit kind of looks like the Greek symbol pi with a lot of imagination. Okay, so that's my RB in a more elaborate model, and this is sort of the bare bones model. Okay, now you want that RB to be not too high, because if it's too high, when I apply a base emitter forward bias, and there's a base current flowing, some of that applied VBE will be wasted across the RB and will not appear across this base emitter junction. Okay, kind of like the source drain series resistance is a problem in the case of a MOSFET. So you'd want this number to be as small as possible. But then, as I just said, if you reduce the base doping to improve the emitter injection efficiency, unfortunately, this also goes up. Okay. While I'm on this slide, I'm also showing this parasitic series resistance of the collector, and you don't want that to be large also. Okay. However, you're kind of in a bind because this collector base junction is generally reverse bias. Therefore, that forces you to make your collector doping to be low. Sorry, collector doping to be low, so that the reverse bias breakdown voltage is high. And that, of course, would increase the RC, which you don't want, okay? So you want to kind of have your cake and eat it too. And the way that's done is you make the collector doping high far away from the junction, but right next to the junction, you make it lightly doped. So that way you can have the benefit of both, because this low P minus doping increases the breakdown voltage between the collector and the base, but farther away, if you make it highly doped, that reduces the RC, okay? It's a more complicated structure, of course, that's described in section 7.1 of the chapter that hopefully you read. And this highly doped region is sometimes called the buried collector or a sub-collector, okay? It's a slightly more complicated process to do that, all right? Now, just for the sake of completeness, we are also showing these various depletion capacitances between the base and the emitter, and the base and the collector. And then you also have diffusion capacitances between the base and the emitter, because that's forward biased. And finally, the most important component, of course, is this input voltage controlled current source. So it's a transconductance GM times VEB is your output collector current, okay? All right, let's go back to the band diagram. So the emitter injection efficiency requires you to make the emitter doping as high as possible and the base doping as low as possible, subject to the constraints of the early effect and the base series resistance, all right? Now, the emitter doping you typically make as high as possible. The limits generally are governed by how much of the emitter dopants you can activate in the silicon, okay? And that's something called the solid solubility limit. So when you implant dopants, there's a thermodynamic limit as to how much you can dissolve the dopants. It's kind of like similar to if you have a glass of water and you keep adding salt, initially all the salt will dissolve in the water, but once you saturate the salt solution, all that extra salt will form a clump of undissolved salt at the bottom. But the same thing happens in a semiconductor. There's a maximum amount that you can dissolve the dopant atoms into the semiconductor. That's called the solid solubility limit, okay? And the emitter is generally doped up to that level. But then on the base, you'd like that to be optimized to make it low enough to increase these components so that the emitter injection efficiency is high, but not so low that the base depletion region extends so much that the early effect is very pronounced. And also you don't want the base doping to be so low that the base series resistance, RB, is too high, okay? All right, what was the other important factor for BJT? That was the so-called base transport factor B. Don't confuse that with the common emitter current gain beta. So these two are different. This is my base transport factor. And that was defined as the collector current that survives the journey at this point divided by the injected current over here. Okay, so that's IC divided by IEN in this case, okay? And that, of course, is governed by the recombination losses in the base, okay? Because when I inject these electrons into the base, some of them unfortunately recombine with holes in the base, and you have to replenish those. So the two components of the base current, IB, are the part that is used to replenish the losses due to recombination, the part due to back injection. The back injection part governs the emitter injection efficiency, and the recombination losses impact your base transport factor, all right? Now, how do I make the base transport factor as high as possible? The highest value, of course, is 1, okay? The best you can hope for is IC equals IE, IEN, not IE, IEN, in which case this curve would be a perfect straight line. In other words, the gradient over here would be exactly equal to the gradient over there, okay? Meaning no recombination losses. How do I achieve that approximately? You make the base width as narrow as possible without suffering from problems like early effect or punch through of the depletion region across the narrow base and so on and so forth. But in general, making the base as narrow as possible improves the performance of the BJT, all right? Now, before I leave the topic of BJTs, I want to introduce a more advanced structure, which is called the Hetero Junction bipolar transistor, okay? Where the band diagram is shown down below. And as you can see in the HBT, you have two different semiconductors, a high band gap emitter and a narrower band gap base and collector, okay? So this would be an example like, you could have, for example, a silicon emitter and lower band gap silicon germanium base as an example, all right? So that you have different barriers because of the different material compositions between the emitter and the base, and the base and the emitter down in the valence band, okay? Now notice, in the case of a homojunction, BJT, as shown on the top, which is what we've been talking about so far, this barrier has to be the same as that barrier, right? Because it's the same band gap everywhere. But if I'm willing to work with two different semiconductors, in the emitter and the base, I can choose material combinations where I could hopefully make this barrier smaller compared to this barrier. This band offset in the conduction band could be smaller than the band offset in the valence band. Okay, how does it help? Well, if I did that, then clearly this barrier for injection of electrons from the emitter to the base being smaller than the back injection barrier, that helps increase this component and suppress this component, right? Without having to play games with the doping that we mentioned before, right? So now you're not forced to make the base doping too low to improve the emitter injection efficiency. Instead, you are making use of the larger band offset for the back injection of holes, all right? And that's what's done in the most advanced HBT structures, in the most advanced BJT structures. And I'm willing to bet that in your cell phones, you probably have one of these silicon germanium, very, very high frequency HBT devices, which handles all the RF signals, communication with the tower, et cetera, okay? In the past, these would be made up of much more expensive compound semiconductor devices such as gallium arsenide, but now, because of progress in silicon germanium HBTs, that's a much cheaper option for doing so. Okay. Similarly, in your laptops, there's a good chance that when you have wireless communication between your laptop and the routers, that's probably done by a silicon germanium, silicon HBT. Okay. The structure for such a structure is shown over here. So here you have a large bandgap silicon emitter, and in the base, I alloy it with a lower bandgap silicon germanium, and that basically modulates these barriers, but this barrier is smaller than the back injection of the carriers, okay? You can also play games where you can modulate germanium concentration, and by doing so, notice that I introduce a slope in the conduction band edge, which corresponds to electric field. In this case, electric field is such, this electric field is introduced by the variation of germanium content, okay? You make the germanium content larger and larger, closer to the collector base junction, and that drift field helps the transport of the injected electrons from the emitter to the base, okay? So that's another twist that is used. Now, just so that you remember how the heterojunction band diagrams are drawn, we discussed that at the end of chapter 5. I'm reviewing that question. Okay. I'm reviewing that for your benefit again. So this figure 5 point something. So this is at the end of the PN junction chapter. Review this very carefully, because in the final exam, I'll probably ask you to draw band diagrams of heterojunctions and analyze that, because it's so important, okay? So how do you do that? Well, if you give you such a problem, what you have to do is you have to know what the electron affinities and work functions and the band gaps are, because with that, you can pinpoint the conduction band edge, the Fermi level, and the valence band edge, okay? So how do I do that? Well, the first thing you should do is you should draw the structure just before contact, which is shown down below. You're not really joining them, okay? And then you first choose the vacuum level, which is this global reference potential energy. And with respect to that, if I know what the electron affinities in the two semiconductors are, I can pinpoint the conduction band edges. Then knowing the band gaps, I can pinpoint the valence band edges. And finally, knowing the work functions, phi in semiconductor 1 and phi in semiconductor 2, I can pinpoint the Fermi levels, right? The work function, remember, is the difference between the vacuum level and the Fermi level, while electron affinity is vacuum level to the conduction band edge. So you first draw that just before contact. And then to draw the equilibrium band diagram, the first thing you should do is, don't worry about drawing the rest of it. You first draw a horizontal straight line and call that your equilibrium Fermi level, right? Because we know in equilibrium, the Fermi level has to be constant everywhere. Okay, so you first draw this line, okay? Then you start drawing the rest of the band edges with respect to the Fermi level, constant Fermi level, not right at the heterojunction, but far away from the junction, because at the heterojunction, that's the most complicated part. You don't know how the carriers are spilling over, what the band bending is, and the band offsets are. But far away, you know that the carrier concentrations will not change before and after contact. So in this case, I've assumed that I have a P-type semiconductor on this side, N-type on this side, clearly because the Fermi level is close to the conduction band over here. Here it's close to the valence band. So I draw it in exactly the same way after contact as before contact, okay? And then the hardest part is, how does the band bending look like at the junction itself, okay? Well, when the bands bend, first of all, you have to make sure that the bands bend parallel to each other, right? Because that's a band gap. So if you end up with the diagram like, something like this and something like this, that's clearly wrong, because that implies that the band gap is changing, okay? And that can't happen. That's a material parameter. So then the important parts are these band offsets, delta EC and delta EV, which were important for the HBT, as I mentioned. Okay, how do you get that? Well, for that, you go back to the band diagram just before contact, and you simply extrapolate the lines, okay? And therefore, delta EC is clearly equal to chi2 minus chi1. So delta EC equals Q times delta chi. That's known as the Anderson affinity rule. So the conduction band edge offset is the difference of the electron affinities, okay? Similarly, delta EV will be equal to delta, it will be chi1 plus EG1 minus chi2 plus EG2, right? So it will be equal to delta EG minus delta chi, okay? But word of caution, don't try to blindly use this formula, because there's a good chance you'll mess up the signs, and you'll get the wrong numbers. Instead, look at the diagram and see how they extrapolate, and you'll know clearly which one lies higher. So you see this is higher than this, and therefore you figure out from this diagram what the delta EV is, okay? And then you figure out how the bands bend. But to do that, remember that electrons flow from the high Fermi level region to the low Fermi level region, while holes flow the other way. So in this case, in this particular case, both this side and this side are getting depleted, and therefore the bands bend as shown over here, okay? So study this very carefully, because there's a good chance I might give you a heterojunction problem. All right, so that concludes our discussion about BJTs. Are there any questions on that?
Professor, I had a question kind of on just course logistics. So I noticed we have a homework due next Monday. I just wanted to make sure that we do indeed have a homework due that Monday after class is finished.
Did I say next Monday, or no? So the final homework is due on Wednesday, this week.
Okay, so we have one due today and one due on Wednesday.
Right. Because if you need a little bit more time for this final homework, I can give that to you. Would you want a bit of an extension? Tell you what, I'll give you an extension. Okay, you can turn it in next Monday. That's fine. Okay, I'll tell the TA.
Okay.
All right. So our final topic is optoelectronics, which involves the interaction of photons with semiconductors. It's a vast topic, okay? And we're not going to do justice to it at all. In fact, the devices that we'll touch upon, things like solar cells, photodetectors, light emitting diodes, and lasers, you could have whole semester courses on each one of those, okay? Obviously, we can do that. It's just a preview of the very, very interesting and important subject, okay? Now, having said that, because we have spent a lot of time on p-n junction diode theory, and that's essentially what's at the root of all these interesting optoelectronic devices, okay? So although we'll not really get into them in gory detail, I will cover the essential physics for all of them. What I'll be leaving out is a lot of the technology, okay? A lot of the engineering, which is very interesting. And if you're interested, there's follow-up courses, both at the grad and undergrad level, that you ought to take, okay? All right, so with that, let me start looking at optoelectronic devices where I take a p-n junction diode and I shine photons on it, okay, with h nu, hopefully greater than the band gap, okay? You have to have that because, it's only when the photon energy h nu is greater than the band gap can I excite electrons from the valence to the conduction band, okay? And I create electron hole pairs. If the h nu is less than the band gap, it simply flows through more or less. Okay, it doesn't create any electron hole pair, so that's kind of boring. Okay, now in this context, you'll hopefully also remember that direct band gap semiconductor with a conduction band minimum, this is the same value of K as the valence band maximum. So that's my K, and that's my energy. That's more efficient than an indirect band semiconductor. Having said that, you can still make optoelectronic devices in indirect band devices, though direct band structures are more efficient. Okay. All right. So what we had mentioned in the context of BJTs, we had basically used this picture to motivate how a BJT operates. Okay, so I'll review that. Okay, and what we had said then was, if you look at a PN junction device and you look at its IV characteristics, in forward bias we have current which goes up exponentially with voltage e to the power QV over KT minus 1. But if the bias is negative, this first term becomes basically 0, and I get minus I naught. Okay, and that's your supply limited reverse leakage current, right? So what you have is, if that's my reverse bias PN junction, say, in high reverse bias, we said that you have a few minority carrier electrons on the P side, a few minority carrier holes over here that diffuse to the depletion edges. And if I have a reverse bias, they get swept right across, regardless of what the reverse bias is, because it's not governed by the drift velocity. It's limited by the supply of these minority carriers, right? But now I can increase that supply by shooting photons at it with an h nu greater than the band gap. So now I create extra electrons and extra holes, and therefore the supply is increased. Therefore, your effective leakage current goes up, as shown over here. So with increasing photon fluxes, you can get more effective leakage current. Okay? And if you operate in that mode, that's what a photodiode or a photodetector is. You basically get an electrical signal which is proportional to the light intensity, which is obviously a very important application, right? You can convert light into electrical signal. Now, when you operate a diode under illumination, we'll consider 4 quadrants. That's called quadrant 1, 2, 3, and 4. And we'll see that depending on which quadrant you operate the thing in, you get different kinds of device functionality. If you operate the diode in quadrant 1, where you inject carriers, so you forward bias the thing now. So now I inject carriers and you recombine the electrons and the holes. These can give off photons, okay? So that region of operation makes it a light emitting diode or a laser. We'll discuss that on Wednesday. If you operate in quadrant 3, which is what I just mentioned, you get a photodiode or photodetector. And finally, if you operate in this quadrant, you get what is called a solar cell. Okay, so it's amazing that my humble PN junction diode, simply depending on which quadrant I operate the thing in, gives me 4 different very, very useful optoelectronic devices. Now, quadrant 2, you don't really operate in that, so it's kind of irrelevant. All right, so let's define, determine the basic equation for such a photodiode. Okay, so what I have over here is my diode IV initially without any light. Okay, so that's my regular diode IV. Some reverse saturation current e to the power QV over KT minus 1. But now, if I shine light, I get an extra photogenerated current component, which I call I optical. Okay, so that's this extra electron hole pairs that are being created, and that results in an extra optical current. Okay, now that optical current, roughly speaking, can be given by the optical generation rate G optical, which has units of number of electron hole pairs created per unit volume per unit time. So number of electron hole pairs per centimeter cubed per second. And this will be basically corresponding to the photon flux, okay? The number of photons absorbed per unit volume per second, okay? Of course, it's generally not going to be a uniform number, okay? Because when I shine photons on it, You'll typically have photon intensity die down exponentially with distance, okay, as we have discussed. So if I look at the intensity I photon, don't confuse that with the current, it'll be some I photon at the surface, e to the power minus alpha x, where alpha is your absorption coefficient. Remember we discussed that at the beginning of chapter 4, okay? Now we'll assume, for simplicity, that that decay is not very pronounced, it's kind of uniform. So we'll assume that I have a uniform photogeneration rate, okay? So in other words, I'm considering thickness, which is much, much shorter than your absorption length. So then the number of carriers that are collected would be this absorption, is this electron hole pair creation rate per unit volume per second times the diffusion length, okay? Why? Well, if I had created carriers very, very far away from the junction, they'll recombine before they reach the junction, right? So it's only carriers within a diffusion length of the junction, Ln and Lp, it's only those carriers which can survive the journey to this reverse bias PN junction, right? If I had created carriers very, very far away, long before they can reach this junction, they'd end up recombining, right? So that's why you have a collection only over a diffusion length or so, okay? That gives you the number of particles that are captured per unit volume. Oh no, and then you have to multiply that by the cross-sectional area. So A times LP has units of centimeter cubed times G optical. So that gives you the number of particles that are collected per second. And then to get the actual current, you have to multiply by the charge of the electron. Everybody with me? So G optical is the number of photons that are absorbed per unit volume per second. So that gives you the number of electron hole pairs created per unit volume per second. Then you have to multiply that by the volume of collection. The volume of collection is the diffusion length times the cross-sectional area of the diode. Okay, so that's the collection volume. That gives you the number of electrons or holes that are collected, the particle number. And then to get the actual current to do that, you have to multiply by the electron charge. Okay, so that gives you your optical current. This term over here, okay? Now you'll notice that the sign of this is opposite to the sign of the forward current, right? Because this kind of corresponds to my increased reverse leakage current, if you will, okay? Now I can write down expressions for both of these shown in the next slide. So the first term is the reverse saturation current of the PN junction diode. This is what we discussed in chapter 5 in great detail, okay? So that's my diffusion lengths times the recombination lifetimes. These are the minority carrier concentrations times the cross-sectional area of the diode and the electron charge, okay? Now this is what we derived using the charge control model. You could also derive it in another way in terms of the gradients of the carrier concentrations. And there you get terms in the form of dP over LP and so on and so forth. And everything else is the same. Now dP over LP is the same as LP over tau P, because dP times tau P equals LP squared. So this is the charge control way of deriving the equation. And this was the way we derived it first in terms of the carrier distributions and the gradients and all that. Do you remember that? Beginning of chapter 5, okay? Anyway, so this is the IV characteristics of the regular PN junction from chapter 5, okay? This is the new term, the optical generation rate. And I'm extending this formula where I'm now collecting carriers on both P and N sides. So those are the diffusion lengths plus the depletion width, W, okay? And we'll assume in a second that the diffusion lengths are larger than the depletion width, W. So we'll ignore that in a second just to make an approximate expression. The optical generation rate is the number of photons that are absorbed per unit volume per second, because in any photon that just flows through, it's not going to help in terms of creating electron hole pairs. And then I get the cross-sectional area of the diode A and the electron charge Q, okay? Now this corresponds to what's called a short circuit current. What does that mean? Well, the short circuit current corresponds to if I took this PN junction diode and I shine photons on it and I simply short circuit the thing. If I short circuit it, what is my voltage across this device? is going to be 0. So I can put V equal to 0 over here. Now what's e to the power 0? E to the power 0 is 1. So for the first term, I get 1 minus 1. In other words, this drops out. And I'll simply have this term. And that's why it's called a short circuit current. Okay. So on this IV characteristics, it basically corresponds to any one of these currents. Okay. So if my applied voltage is 0, that's how much current will flow across the device, depending on the photon flux. Okay. And that will be responsible for the short circuit current in what's called a solar cell. We'll see that in a second. The other important parameter is called the open circuit voltage. Well, if I have an open circuit voltage, how much current can flow in this loop? Clearly that's 0, right? So now I set I equal to 0 if I want the open circuit voltage, and I solve for this voltage over here. Okay. Now you basically have to invert this by setting I equal to 0 and solve for the voltage using this expression. Now you end up then getting a pretty messy looking expression, and that is the accurate expression, but you can simplify that. Okay. So I set I equal to 0 and I solve for this voltage over here from here. That's my open circuit voltage. Okay. But then you can kind of approximately simplify that to get a sense of the physics by assuming first that the depletion width W is much, much smaller than the diffusion length. So I kind of ignored that, say. Okay. And then you also assume that it's a symmetric structure where the diffusion lengths LP and LN are the same on both sides. The lifetimes on the two sides are the same, none of which is true, okay? Because we've seen that, for example, electron mobilities and diffusion lengths typically are longer than hole mobilities and diffusion lengths. So in general, LN will be larger than LP, okay? So this is just an order of magnitude type of estimate of the physics, okay? So let's pretend that these parameters LN, LP are the same on the two sides, the lifetimes tau N, tau P are the same, and then PN, NP are also the same, so have comparable dopings, just to get a rough idea, okay? And then I've ignored the W, so what do I get? Well, if I made all these highly simplifying assumptions, what you find is, oh, and furthermore, I assume that I have a large photon flux, so G optical is very large, so I can even ignore this 1 at the end. So then this simplifies to this, okay? So I basically get G optical by everything left over here, and that can be written as G thermal, okay? Why is that G thermal? Because it's of the form LP tau G thermal is equal to LP PN over tau P, for example, or LN NP tau N. Okay, and if you look back at your PN junction theory, that is nothing but your thermal generation rate of carriers. So that's why it's called the G thermal rate. Okay, so that's the term because of this black body radiation that I can't do anything about, while the numerator G optical is this extra light shining on it. Okay, so what it tells you is that the output voltage, the open circuit output voltage, that corresponds to, if you continue these curves, that corresponds to the current I being 0. That's how much voltage develops across an illuminated PN junction. And all of this is relevant for solar cells, okay? Is given by this. What you find is, because it's a logarithmic dependence on light intensity over G thermal, as I increase the light intensity, the open circuit voltage sort of saturates. In fact, it will saturate at the built-in voltage, as we'll see in the next slide. Okay. So that equation is important to solve numerical problems. Okay, so make sure that you understand that. The next slide kind of gives you an idea of how you operate the device in different quadrants to get different functionality. So once again, that's quadrant 1. That's what gives you a so-called light emitting diode or a semiconductor laser, where the PN junction is forward biased, as shown over here. Okay, if you forward bias the junction, I inject holes this way and electrons this way. Okay, and in this forward bias junction, as I inject holes, sorry. So as I inject, electrons this way and holes this way, these electrons and holes can recombine very effectively, especially if it's a direct band gap semiconductor. And they recombine, they'll give off photons of light, as in a light emitting diode. Or if the light that comes off is all in phase, that version of a light emitting diode is called a laser. Okay. Now, lasers are a very important topic, but it's somewhat complicated also. So in this course, we'll not be responsible for them. But on Wednesday, I'll very briefly tell you about how lasers operate. Okay. So it's sort of a laser is kind of like an LED, where the light that comes off in an LED is in random phases, but in a laser, the photons that come out are all in lockstep and barrel. Okay. So the analogy that I use, had we been in class, is an LED is like students at UT, while a laser is students at Texas A&M. And what I mean is, when I dismiss class, you guys kind of walk out of the classroom in random phases, right? While if I taught the class at A&M, a lot of them are ROTC students and are very well disciplined, so they'll march out of the classroom in lockstep, kind of photons in phase. All right. Now, if I operate in quadrant, so that's quadrant 1. Quadrant 2, there's nothing that happens over there. That's quadrant 3, and that's quadrant 4. So in quadrant 3, I end up getting basically a leakage current that's proportional to the photon flux. And that's what I use in a so-called photo detector or photodiode. Okay. I'll hopefully get to that at the end of this class, or maybe on Wednesday. Okay. This is what I get, as I said, a solar cell. So let's start off with that. Okay. So in a solar cell, you don't bias the PN junction. You shine photons on it, hopefully from the sun, and you get an output out of it. So you basically are using the PN junction diode as a battery. You're using it as a source of electrical power. Am I creating electrical power out of nothing? Obviously not. I mean, you can't violate energy conservation principles. You're converting a part of the solar energy into useful electrical output. So in this configuration, the current direction actually points opposite to a forward bias diode. So in a forward bias diode, you apply the positive terminal to the P side, and you flow current this way, right? While in a solar cell, when I shine light on it, the current actually comes out in the opposite direction, as you can see, to that in a forward bias diode. And that can be seen in this IV characteristics also, because here the polarity of the current is positive in an LED, while here the polarity in a solar cell is opposite to that. Okay, so that's a quadrant that we want to talk about in more detail in the next slide. Okay, but before I go to that, this is the solar cell IV, but here in the IV, I have flipped the figure by, I made it upside down. So the solar cell IV is this part. In the next slide, I flip it by 180 degrees. So this curve looks inverted like this, okay? So when I go to that, don't get confused by this IV. All right, so for this solar cell, the two important parameters are the short circuit current and the open circuit voltage that I derived in the previous figure, all right? Now those are shown in this band diagram for this illuminated solar cell. Okay, so I shine light on it, and I basically have developed a forward bias in open circuit, which is equal to the VOC. Okay. Now, how do I get current flow in such an illuminated junction? When I'm shining light on it, I'm creating electrons and holes. Okay. These holes diffuse towards this. Electrons diffuse this way, as I mentioned, right? And the holes then flow out at this end, and the electrons flow out at this end. Okay? And that's what I have over here, right? So the holes flow out at this end, and the electrons flow out at this end. But if the electrons flow out this way, the current, of course, is opposite to that. And that's how the current flows in a solar cell. Okay. Now, higher the intensity of the light, the bands effectively get more and more forward bias. Okay. And this VOC increases. Okay. Now, how much VOC can I get out of it, theoretically? Well, with very, very high forward bias in an asymptotic limit, this barrier essentially vanishes. Therefore, this VOC that you can get, the theoretical VOC that you can get, at most is equal to VO, which is this built-in junction voltage, okay? Which in turn, the asymptotic limit of that is equal to your band gap, right? So in a solar cell, the maximum possible output voltage in open circuit that you can get asymptotically would be equal to the band gap of the semiconductor. So in a silicon solar cell, that would be at most 1.1 volt. Of course, you generally don't even get that because your V naught is going to be less than that. The typical output voltage is in a silicon solar cell will be of the order of 0.7 volts or so. Okay. Okay, now let's dive deep into the solar cell physics. And the important band diagram, once again, is this one, right? And I'm operating in this regime where I basically develop a forward bias and I'm driving current out of the PN junction. And I'm using this basically as a battery, okay? So that's the technology I'm looking at. And as I said, and I could spend, frankly, a whole semester talking about the engineering of solar cells, I only highlight some of the more important parameters, okay? But to understand the important parameters, you have to look at the intensity spectrum of sunlight, okay? Now, this is not current, it's a light intensity as a function of the frequency of light, okay? So if you look at the solar spectrum, you'll have some sort of a distribution like this. It's just approximate, okay? So you have maximum light intensity from sunlight at some frequency. And then as you go to higher and higher frequencies, this is the ultraviolet part of the spectrum. This is the infrared part of the spectrum, okay? And then if I choose a particular semiconductor with a band gap of this much, say Eg, what's going to happen? Well, any photons with the band gap, with the energy less than Eg, will simply shine right through, right? So this part of the spectrum will be wasted. So what do I want to do? Instead, I want to choose a band gap so that I capture most of the solar energy, right? But there's unfortunately a problem with that because if that was the only issue, you could say that, I choose a semiconductor with essentially zero band gap so that I can capture the entire solar spectrum. So why don't I do that? Okay. Well, the problem is the following. This is the band diagram. Suppose I have a band gap of this much, and I choose photons of different energy, increasing photon energy. What's going to happen? Well, if I choose, suppose this is my band gap that I've chosen, right? If I choose a photon with a slightly higher energy, it'll do this. I'll create electron holes, and that will hopefully give rise to useful output, electrical output power, okay? On the other hand, if I choose a photon with a much higher frequency, say nu2, what's going to happen? I excite electron hole pairs like so, right? Is this electron got a lot of kinetic energy or not compared to this electron? Clearly does because it's much higher than the band gap, right? So this highly energetic electron or so-called hot electron will rapidly lose its energy by colliding with defects or phonons or whatever. Simply the hot hole will lose its energy very quickly. And then it will recombine and it will give off a photon where the photon energy will be comparable to the band gap. So regardless of whether I've absorbed a low energy photon, h nu1, which is slightly higher than the band gap, or a much higher energy photon, I get one electron hole collection, right? So what I'm trying to tell you is all that extra photon energy is being wasted, right, as heat in the solar cell. I'm not getting any more electrical output out of it. All right. So the guys who first analyzed this problem are my old friends, William Shockley and Quasar, and they derived what's called the Shockley-Quasar theoretical limit. And they said that, if you look at the solar spectrum, you have to sort of optimize your band gap. So you want to capture most of the photons, of course, but you don't want too low of a band gap so that you waste a lot of this extra photon energy as heat, right? So there's some sort of a sweet spot which will maximize the efficiency of a solar cell, a single junction solar cell. And that limit for a single junction solar cell is approximately 30%, okay? And luckily for us, that optical band gap roughly corresponds to the band gap of silicon, about 1.1 eV, if you match that with the solar spectrum, okay? Now the solar spectrum, of course, depends on where I am on the surface of the Earth and the time of the day, right? Because if I was on Mount Everest, where the atmosphere above me was thinner than at sea level, I'll obviously get a higher intensity, right, of solar radiation. Similarly, if this is my Earth, and the sun, and it's covered by this atmosphere, suppose I'm at this location over here in Austin, okay, where the sun is shining head on at midday, I get a higher intensity than early in the morning, where the sun has to pass through a larger portion of the atmosphere, or in the evening, right? So all of this are captured in solar cell physics in terms of defining the intensity as so-called air mass zero. Air mass zero is the highest possible intensity that I can get without any atmosphere at all. So that will be sort of in outer space where the sun is shining on the solar cell head on. So if I'm on the International Space Station, there's no absorption by atmosphere, and suppose my solar cells are pointing straight at the sun, that's the maximum output that I can get with air mass zero. Okay, of course that's not practical for terrestrial applications. So then you can say that, okay, on the surface of the Earth at sea level, if it's shining head on, I call that air mass 1. Okay, so that's all the atmosphere absorbing the sunlight, but the sun is overhead. Okay, but of course that's right in the middle of the day. At sunrise or sunset, I'll obviously get a lower solar intensity. So what's done is, typically when you characterize the solar cells, you assume some sort of an average, say, at maybe 9 o'clock or 3 o'clock, and you assume an air mass of 1.5. Okay, so that's sort of not the best case, not the worst case, and you look at the solar intensity profile at air mass 1.5. So if you read the literature, that's what the terminology means, okay? So that's one point. Point number 2 is you want to choose a band gap so that you capture most of the solar radiation without wasting a lot of the extra solar photon energy as heat, okay? And that gives you your Shockley quasar limit. Now, if I had infinite amount of money, like NASA, of course, they don't have infinite amount of money either, but they certainly have more money to spend on the solar cells on the International Space Station than you or I do if we wanted to put solar cells on our rooftops. So for NASA, they're not stuck with a single PN junction, with a single material, okay? What they will do is they want to maximize the efficiency. And what they make are what are called tandem solar cells. And basically what that involves is you have multiple solar cells with different band gaps, okay? And there, what's done is you shine photons at this end, say, which has a whole bunch of photon energies. In the first PN junction, you absorb these photons, okay? But then the lower energy photons simply pass right through. These are absorbed by the next layer of PN junctions, okay? Then the lower photon energies pass through and they shine and absorbed by the next layer of PN junctions. So basically you have multiple PN junctions with decreasing band gaps, and you shine it from the top. So the highest energy photons are captured by this PN junction at the top. The lower energy photons pass through, then they're collected by the next PN junction, and so on and so forth, okay? And as you can hopefully see qualitatively, the more PN junctions that I stick in series or tandem, and I optimize the band gaps to match the solar spectrum, I can improve my solar cell efficiency, okay? And the champion numbers these days for the most advanced solar cells made up of gallium arsenide, which is a direct band gap, unlike silicon, which is indirect, you can achieve efficiencies of the order of 50, 60%, okay? The problem, of course, is, these structures are obviously much more complicated. You also have to worry about current matching because the solar cells are in series. So you have to optimize the thicknesses so the current is more or less comparable throughout the whole structure. Very, very complicated structures, very, very expensive, and therefore it's not practical to use them in terrestrial applications. So for most terrestrial applications, you work with silicon because it's a very abundant, cheap material. And even though it's an indirect bandgap semiconductor where the absorption efficiency is not going to be as high as for a direct bandgap semiconductor such as gallium arsenide, absorption is good enough. And if you look at the cost-benefit ratio, and that's sort of the technique of the device of choice for mainstream terrestrial applications, okay? So all your rooftop solar cells are made up of silicon solar cell. But if cost is not an issue, and you want to maximize efficiency, especially for NASA, you can use compound semiconductor tandem solar cells. Those are two of the extreme limits, if you will. Now let's look at the structure of the solar cell and see what the issues are, okay? So here, I'm looking at the IV of the solar cell. I'm looking at the IV of the solar cell, but I've flipped it by 180 degrees. So I'm flipping it. So that's what I'm showing in the fourth quadrant, okay? But it's flipped upside down. So once again, that's my short circuit current, and that's my open circuit voltage. Now on this solar cell, I'm basically using it as a power source or a battery. I have to choose a suitable operating point. And what that means is I have to choose a load resistor, which will determine at what point I'm operating the solar cell in, okay? So suppose I've chosen a resistor so that I flow a current IM, and I get an output voltage under those conditions of VM. The power that I get out of the solar cell at that operating point is IM times VM, okay? And you, of course, want to maximize the power extraction from the solar cell. So you choose the largest area rectangle that you can inscribe in this IV characteristics of the solar cell. So that determines what's called the fill factor of the solar cell, okay? So that's the maximum operating point and the maximum power output, IM times VM, divided by I short circuit over V short circuit, okay? So basically what it means is, depending on the solar cell, you don't want to operate at this point, for example, because then the area under the rectangle is much smaller than this maximum operating point. It also tells you that to maximize this fill factor, which is sort of a measure of the efficiency of a solar cell, you want this IV characteristics to be as rectangular as possible. Instead, if you had an IV, which is kind of like this, the maximum area rectangle that you can inscribe in over the area ISC, VOC, that ratio would be smaller, right? So more square-like this IV is, the better off you are in terms of a higher fill factor, okay? The more like this, the IV is, the worse off you are. You can't extract as much electrical output power of the solar cell. Now, without going into the details, one can show that the lower the series resistance, internal series resistance, RS, of my solar cell, the more box-like the IV would be. The higher the value of the series resistance, more like this, the IV becomes, okay? And in fact, it's very similar to the issue that you have in a regular battery also, okay? So in a battery, the output voltage that you get out of it will depend on the electrode materials in the battery and the electrolyte that you have in the battery, okay? And interestingly enough, that output voltage does not change. The open circuit voltage does not change. Instead, what happens in a battery as you consume more and more of the material, suppose it's not a rechargeable battery, maybe it's just a regular alkaline battery, as you have more of this electrochemical reaction that goes on, this internal series resistance of the battery keeps increasing, okay? And that's what causes you to, get rid of the battery, not because of VOC changing, but rather the internal series resistance keeps increasing, okay? And if the internal series resistance increases too much, then if you hook it up to an external load resistor, and I'm trying to flow a current, more and more of the voltage output is wasted across the battery itself, right? Which is I load times the internal series resistance of the battery. That goes up, and when RS goes up high enough, that's when the battery kind of becomes useless, okay? So it's the same kind of physics over here. You basically want the RS to be as small as possible, okay? Now, how do I make the RS as small as possible? Here, you face a technological problem. To understand that issue, let's look at the cross-section of a solar cell and the corresponding top view, okay? So on the left, I'm looking at the slice of a solar cell. I have my PN junction. And on the right-hand side, I'm looking at it from the top, okay? So that's the top view. Okay, where these dark regions are my metal contacts, my ohmic contacts in this case, to the N side, which are shown as fingers over here, say. And then on the P side, you can assume I have a ohmic contact on the back side of the solar cell. All right. Now you may recall from your PN junction theory and theory of ohmic contacts that to reduce the contact resistance, you want the area of the contact to be as large as possible, right? In other words, you want these fingers to be as large as possible, right? Because larger the contact area between the metal and the semiconductor, hopefully the lower will be the resistance of the device. Now, following that logic, why not have this entire surface covered by metal, right? On the top surface, because that gives you the maximum contact area that would minimize your RS and it would make your IV more and more box-like. And therefore that would help improve the fill factor. What do you think the problem is with that? Well, that can be seen if you look at the left-hand side, because if I was to cover up the whole thing up with metal and I shine photons on it, would that go through the metal? Obviously not, right? So that causes shading. So that's the first engineering design parameter. You want to kind of optimize these fingers to minimize your RS as much as possible, but at the same time not cause a lot of shading, okay? Now there's other technological tricks that are used also. People use transparent conductors, which are electrically conducting, but allow light to go through. And one of those is a material called indium tin oxide. Nowadays people are exploring this new material called graphene, which is electrical conductor, but doesn't absorb light as much. So there's all kinds of engineering issues. And as I said, if you're interested, take a course taught by Professor Dodha Balapur. He teaches that, I think, every other semester, where the basic PN junction theory I've already discussed, but all these technological details are very, very interesting and very, very useful also, okay? Now, I'm sure you're aware of, all these issues about climate change and alternative energy, et cetera, et cetera. And people on the right will say that, you can't get rid of fossil fuels and alternative energy like solar cells or wind doesn't make sense with solar cells. For a long time, the criticism was, if you look at solar cells, it consumes energy to make the solar cells, right? So first of all, you have to grow the silicon crystals, okay? And that's a high energy intensive process. You have to melt silicon dioxide and coal. This is what we discussed in chapter 1. You fire it up in a furnace, which operates at close to 2000 degrees centigrade. So you have to sort of add up all the energy required to grow the crystals, make the solar cells, et cetera, okay? So if you add up all the manufacturing energy input, you have to match that with how much energy you can get out of the solar cell, right? So that is governed by what's called the kilowatt hours. So the kilowatts that you can generate from a solar cell array times the number of hours it operates for, okay? So kilowatt has units of power, and times the operating time in hours gives you units of energy. So you have to determine how many kilowatt hours of energy you can get out of a solar cell, right? So that, of course, will depend on, the number of hours of sunlight times the lifetime of the solar cell, right? And in the earlier days of solar cells, the efficiencies are not very high enough. And in fact, the total integrated energy output that you could get out of the solar cell was initially actually lower than the energy input to make the solar cell, and then it became comparable. But now, with improvements of solar cell efficiency, you can get silicon solar cells with an efficiency of, say, 25% or so, which is close to your Shockley quasar limit. Now, the net integrated output is actually much higher than the energy input required to make the solar cell, okay? And in many cases, the cost of electrical output from solar cells is in some cities and states lower than the cost of generating electricity from fossil fuels. Okay, forget about climate change and all that. I mean, the raw cost of energy output from silicon solar cells or wind energy, which of course is not a topic of our course, it's less than energy costs from fossil fuels. Okay, but there's a big catch, of course, right, with silicon and wind, and that catch is it's intermittent, right? I mean, the sun is not going to shine at night. If you have cloud cover, the output goes down. Similarly, wind, wind doesn't blow all the time. But luckily, statistically, people have found that if you co-mingle in the same land area, wind turbines and solar cells, people find that statistically, the wind tends to blow more at night while the sun shines during the day. So if you have a mix of wind and solar, kind of evens out the solar output, the solar plus the wind output. But even then, you can certainly have scenarios where you don't have sun shining or the wind blowing. So what do you do then, right? So then on these grids, you always have to have a backup power. And that, unfortunately, in many cases involves fossil fuels or nuclear energy. And the problem there is with this, suppose I have a coal-fired plant, you can dial up and dial down these coal-fired plants very, very quickly. So you kind of have to operate that at a certain baseline level to kind of even out these fluctuations of output from solar or wind, et cetera, et cetera. So it's not an easy task, okay? So one solution that's been proposed is, if you could somehow store the energy, you could use that to kind of smooth out the output, right? Of course, with solar, that would be batteries. Unfortunately, if you look at the total number of batteries that have been produced in the world and are in use today, the total integrated energy of all the batteries at this point correspond to basically 1 day of energy use in the US. So, battery storage is also not a easy problem. But, hopefully some of you, if you get into this field, you'll make advances in storage and improved energy generation, so on and so forth, okay? Okay, so much for my pep talk for alternative energy. A few other physics issues. So when you design the structure, you need to make the junction such that the junction depth in this case is shorter than the diffusion length of holes, because when I absorb the photons, okay, the light intensity dies down like so. I'll generate more electron hole pairs over here. You need those holes to be able to diffuse to this junction so that they can be collected by this junction. That's why you want this diffusion length to be larger than the junction depth, right? Because if the diffusion length was much, much shorter, yeah, you generate electron hole pairs, but they recombine well before they reach the junction. That's obvious, right? The other important parameter is you want the absorption length, 1 over alpha. So when the light is absorbed, we saw that in chapter 4, it dies down as some I naught e to the power minus alpha L, right? L is the distance. So it dies down exponentially. If you have a large absorption coefficient, it will die down rapidly. A short absorption coefficient will die down more gently, okay? You want this 1 over alpha, this absorption length, to be less than the diffusion length of electrons, okay? What that means is, when I create, I want the absorption to be within diffusion length of electrons in this p-n junction, because if the absorption length is very, very short and something like this, and I create electron hole pairs over here, these electrons can diffuse all the way to the junction. So there's all kind of very, very interesting device optimization issues for the solar cells, okay? And then finally, of course, you have to match the band gap to the wavelength of the solar spectrum, and that's what I've discussed already. Any questions? All right. So the next topics that I'll cover quickly in the next class are photodiodes and light emitting diodes. The basic device physics I've kind of covered already. Now, what are these used for? Well, one major application of these devices are in optical communication, as shown in this figure, okay? Now, as I'm sure you know, that the vast majority of communication in the world today is optical, okay? And that can be seen in this overview slide, if you will, okay? So if I was to send an email, for example, to my friend in Europe. Okay, I type up my email, for instance. Okay, or maybe I'm doing FaceTime with a friend, right? So this analog input, which is my video, would be converted to a electrical signal through some sort of an A to D converter. Okay, the analog signal is converted to a digital signal, and then that is used to modulate a light source, such as a semiconductor laser, or maybe an LED. And a laser is typically what's used. Okay, and what the laser is used for is you convert this digital ones and zeros into light pulses, as shown over here. So every digital bit 1 corresponds to a light pulse, as shown over here. Zeros, no light output on the laser. Okay, these light pulses are then transmitted down what are called optical fibers, which operate on the basis of total internal reflection. What is that? Well, you remember from your freshman physics that if you have a high refractive index medium such as glass and low refractive index air, and I shine a light ray, the angle over here will be larger than the angle of incidence, right? And that follows Snell's law. As I increase the angle of incidence, at some point it will reach the critical angle, and beyond that point, the light will be totally internally reflected, right? So when this angle of incidence is greater than some critical angle, I have total internal reflection of light. When I go from a large, high refractive index medium to a low refractive index medium. That's the basic physics of optical fibers. You make them out of glass. So if you launch these laser pulses at an angle greater than the critical angle, instead of going out into air, it'll bounce back, it'll keep bouncing back, okay? And that's how you transmit the signals over enormous distances. So, you have these submarine cables that go under the Atlantic or Pacific, and that's what carries most of the information in the world today. Or when you go from one city to the other, it's all optical, okay? Now, unfortunately, although these glasses are made very, very cleanly so that there's very little absorption of the light, after you propagate the light for maybe several miles, the intensity will drop. So you have to periodically convert the light back into electrical output, amplify the electrical signal, use that to convert that back into high intensity optical bits, okay? So these are the repeaters, okay? Then you have switching circuit. So, you switch it between, say, I launch it from Austin, and then switching circuits which route it to maybe Dallas or Houston, okay? Then at the other end, you have to convert the light output into electrical signal, and that's where the photodetectors or the photodiodes come in, okay? You have things like low noise amplifiers. You reshape the signal. So by the time it propagates a long distance, okay, these clean bits may not be clean bits. They may be, very distorted bits. So you have to make sure that you use what are called regenerators so that you can decode them properly. You have a decoder, converts the digital signals back into analog signals, and then you get a video output, FaceTime, okay? So in this class, we'll focus on the sources, the LEDs or the lasers, and the photodetectors, okay? But before I do that, a little bit more about these optical fibers themselves to see what the issues are. So these optical fibers, as I said, you have a high refractive index medium, and outside, of course, you have air with the refractive index is 1. Now, generally speaking, you don't want a glass fiber. These are very, very skinny. I'm sure you've seen this. It looks like hair exposed to the air, because then any surface roughness can cause the light to be scattered out. In fact, if you look at these cheap optical fibers in toys and you shine light at one end, you can actually see some light through the optical fiber, and that's bad, right? That means that the light is actually scattering out. So to prevent that, you actually cover the core of the optical fiber with what's called a cladding layer. Cladding layer. But the cladding layer has a refractive index lower than in the core, but it's still higher than in air, okay? So what that does is it restricts the light within the fiber itself, and you don't reach the air fiber interface where I'm susceptible to light leaking out, okay? And for the cladding, you can have a sharp change as shown over here, or actually a better design is a gradual modulation of the refractive index, okay? And you can do that by putting in impurities into the glass which change the refractive index in a nice smooth fashion. And if you do that, you have a graded optical fiber. And the nice thing is, and then you get constant refocusing, kind of like in a lens, okay? And that causes less scattering. Now, these optical fibers are basically made up of glass, SiO2, but very, very clean glass, okay? But even if you make it very, very clean, you'll always have some scattering or absorption of the light, okay? And people have studied this in gory detail. And one of the culprits is OH hydroxyl groups in glass, okay? And the net upshot of that is, if you look at the attenuation in decibels per kilometer of travel of the light, shown on a log scale. So this is a log scale. As a function of the wavelength of light, as a function of the wavelength of light, you see that the attenuation peaks at certain wavelengths and has a dip at certain wavelengths, okay? Now, do I want to propagate the signal where I have absorption dips or peaks? Clearly, I want it to be at dips of the absorption, right? Because that means that I can propagate the signal for a longer distance before I have to do this complicated regeneration, et cetera, right? So for glass optical fibers, the two dips are at wavelengths of 1.55 microns and 1.3 microns, okay? And that is why in this field of optoelectronics, there's been a lot of work trying to have nice light sources and photodetectors at these two wavelengths. Okay, these are your so-called telecom wavelengths. Okay, 1.3 microns, 1.55 microns. Okay, so if you get into the field, if you are able to develop better sources or photodiodes which operate very well at these two wavelengths, you'll be rich and famous. On Wednesday, I'll wrap up optoelectronics very quickly by talking about photodiodes and light sources. And then, we'll save time for any questions. I'll tell you about the final exam, so on and so forth. Any questions? All right, see you on Wednesday.